continue with section 12.3. This is part 2. And we're now going to look at infinite limits. At a boundary point, we've already seen that typically if we attempt to substitute our values in and we get an indeterminate form, like 0 over 0, we can usually do some algebra and find a finite limit. However, what if we try to substitute our values in and instead we get some non-zero number over 0? That's an indication that the limit is probably infinite. If you think about it, think of a finite number, like say 5, divided by something really, really small, like a millionth. 5 divided by 0.00000001 is a very, very large number. The limit becomes infinite. Let's take a look at this example. I want the limit as x and y go to 1, 1 of 1 over x plus y minus 2. We've actually already talked about the domain of this function. But let's do it again real quick. Our domain, x plus y minus 2 can't be 0. So we can't have anything on the line x plus y equals 2. And the domain would be everything else. All right. If we try first of all, let's talk about the point itself. The point 1, 1, clearly 1 plus 1 does equal 2. The point 1, 1 is a boundary point. So not surprisingly, we're expecting trouble when we try to substitute this in. But we'll try anyway. And when we do, we get 1 over 1 plus 1 minus 2, or 1 over 0. Okay? This is exactly what we were just talking about. A non-zero number on the top, divided by a number really close to 0, tells us this is going to be an infinite limit. That's about the best I could do right now. Although we could look a little bit more both at the graph, which we'll do in a minute, but also thinking again back to our domain. All of the points up here satisfy the property that x plus y, well, actually, let me do it this way. No, we can do it that way. X plus y is greater than 2, right? 2 plus 2 would be 4. That's greater than 2. Whereas everything over on this side would satisfy x plus y is less than 2. So, if I approach this boundary from above here, I'm going to have positive values for my denominator. I'll have x plus y's that are bigger than 2. I'll subtract 2. I'll get a positive value. So on this side, I would expect, since I already know it's an infinite limit, I would expect this side to go towards positive infinity. So from above the line, x plus y equals 2, we expect to go toward positive infinity. And we expect to go towards negative infinity from below. Again, if you think about it, if x plus y is less than 2, I'd have some number less than 2. Subtract 2, that's going to be negative. I already know it's an infinite limit, therefore it must be negative infinity. Let's take a quick glance at the maple graph of this one. Sorry. There we go. All right. If we take a quick glance at our maple graph, here it is. There's 1 over x plus y minus 2. Remember this one? We saw that domain was excluding that line x plus y equals 2. And let's see, let me get this turned in the way that we expect to see it. Almost there. There we go. So here we are above that line. Here we are below it. If I go turn to the side, you can see our curve going up towards positive infinity from this side, which was above that line, and then down toward negative infinity on the other side. So up towards positive infinity, going down toward negative infinity, just like we predicted. All right, back to our pencil paper here. Let's do one more like this. This time I'm taking the limit as x approaches 0, 0, and my function is 1 over x squared plus y squared. As far as the domain, I know my denominator can't be 0. But keep in mind, because these are squared, these are both positive numbers, right? The only way that x squared plus y squared could ever be 0 is if x and y are both 0. Any other values, positive or negative, once you square them, will result in a positive plus a positive, and therefore won't be 0. So that's the only bad point. That means if I wanted to sketch my domain, it's basically like having a little hole right here at the origin, and the domain is everything else. All right, naturally, the point that we're interested in is 0, 0. It's the only bad point in the whole graph. It would qualify as a boundary point. It's a missing point on the graph. So 0, 0 right there would be a boundary point. I therefore will expect that when I try to plug it in, something bad is going to happen, and of course you can see this one pretty easily. If I try substitution, I would get 1 over 0 squared plus 0 squared, giving me 1 over 0 again. And as soon as I see that non-zero over 0, I'm going to conclude once again that we have an infinite limit. Just like before, the only question that's left is, can I predict whether it's a positive infinity or a negative infinity? And in this case, that's pretty straightforward. That denominator is always positive, right? It'll never be negative, so I must be going to positive infinity. So this time I can say the limit is positive infinity, no matter which way I come at it from. And if we look back at a graph of this one, there it is. There's my 1 over x squared plus y squared. Here's my graph. We saw one like this when we were doing level curves, right? You can see there's that missing point. It doesn't exist right at the origin, right? There's no z value when x and y are 0, 0. But clearly, this graph is going up, very steeply in fact, towards positive infinity as we get closer and closer to the origin. All right, so that's two situations. One, again, was what happens when we approach, or when we have an indeterminate form, 0 over 0. That's when we do some algebra. Two was, what if we get a non-zero number over 0? That tells us infinite limit. There's a third possibility. Sometimes we have limits that don't exist. Other than the limits becoming infinite, can you remember from Calc 1 what else might cause a limit to fail to exist? Remember those jump discontinuities? where they approach one thing from the left and something else from the right. Graphically, they might look something like this. Right here, at whatever x value this is, I'll just call it a, we have a jump discontinuity. The way we knew that we had a jump discontinuity based on the limits is when we approached a from the left, we got one limiting value, and when we approached a from the right, we got something different. So maybe I'll just call this M, and I'll call this one N. The limit is we approach a from the left, would have been M here, and the limit is x approaches a from the right, would have been N. We get different values from the left and right. That was pretty much the defining limit that told us that we had a jump discontinuity. Could we, and in that case, then we had to say the limit does not exist. Okay, could we have a similar situation with a function of two variables? Well, let's imagine again what those graphs look like, right? The graph of a function of two variables is a surface. So how, if our graph up here is some kind of a surface, I'm just going to sort of say that in general right now, and I'm approaching, excuse me, I'm approaching some point xy, what would be the equivalent of a jump discontinuity? Well, essentially what would have to happen is as I approach this point xy from one direction, I have to get some value, and as I approach it from another direction, I have to get a different value. But here's where it gets a little bit more complicated. In the two-dimensional situation, I was only able to approach a from the left and from the right. How many different ways are there for me to approach this point xy? There's infinitely many ways to approach that point, right? So all I have to do is show that there are at least two different ways to approach that give different answers. There might be 10 different ways or 50 different ways to approach that are going to give me different answers, but if I can just find two to get a contradiction, that will be sufficient to say that the limit doesn't exist. So my goal here is to find two ways to approach the point xy that give different limits. Then I can conclude that the limit doesn't exist. The problem is because there are infinitely many different ways to approach, sometimes it takes just a little bit of ingenuity and often some trial and error in order to figure out the two paths. So that's what we're going to work on in the next couple of examples. In example 3, I've got the function 4x minus y over 3x plus 2y, and it specifically in the directions tells me to show that the following limits fail to exist by demonstrating that you get different limits on two different approach paths. For the purposes of this class, I will always tell you when the limit's going to fail to exist. You won't have to figure that out on your own. It's just takes a bit more practice, I guess, than the time that we have to do this with. But I will notice if I tried to plug in 0, 0, I would get 0 over 0, an indeterminate form again. Usually when that happens, our solution is to do some algebra, but you might notice here there's really nothing to be done, right? I can't factor anything. There's no conjugate to multiply by. There's no trig to simplify. There's really nothing I can do to that, which is the first thing that makes me suspicious that it's probably going to fail to exist. But they told me that in the instructions anyway, so we're good to go. All right, let's think about the domain. Three x plus 2y not equal to 0. So y is not equal to negative 3/2 x. So there's the line y equals negative 3/2 x. And I'm putting that in as a dotted line. Since I cannot have any points on that line, they would cause my function to have 0 in the denominator. Everything else is in the domain. And my goal is to approach the point 0, 0. So 0, 0 right here on my line is a boundary point. Not surprisingly that we got that, that nothing great happened when we tried to substitute it in. All right, since this time our goal is to try to find a point, or to try to find two paths rather, that give me different limits, I'm going to pick two ways to approach that point. I'm going to approach, first of all, let's say along the x-axis. So I'm heading towards the point 0, 0 along the x-axis. Path 1, x-axis, or in other words, y equals 0. Okay. Since I'm using that axis, every point on there has y equals 0, I'm going to go back and redo my limit. But I'm going to plug in y equals 0. And of course now I get something that I can simplify. 4x over 3x is just 4/3. So along the first path, my limit is 4/3. Now let's try another one. Let's use the y-axis this time. What if I try to approach my point 0, 0 along that y-axis? Of course, the y-axis would have equation x equals 0. So I'd have the limit as xy approaches 0, 0. And this time when I write down my function, I'm going to go ahead and substitute in x equals 0. So I'd have 0 minus y over 0 plus 2y. And you can see that negative 1/2 is what that's going to simplify to. And so we've done exactly what we said. We've approached the same point both times. You have to approach the point in question. But as we've approached that point from different directions, we actually got two different limits. This is the three-dimensional version of approaching from the left and the right, like we did in Calc 1. So this is a contradiction. Telling me that my original limit fails to exist, does not exist. All right, we're going to take a look at a graph here. All right, here we go. Here's our function, 4x minus y over 3x plus 2y, graphed over here. And you'll notice right through there, there's that sort of a gap. That's going to be that line that's missing, that y is not equal to negative 3/2 x. What you have here, this little crinkly thing, isn't really part of the graph. That's just, again, sort of that attempt at an asymptote that doesn't really exist, but oftentimes technology will show. All right, I'd like to be able to see these limits. And the first thing we approached was along the x-axis. Here's my x-axis right here. So I'm going to turn my graph until I'm essentially looking straight down the x-axis. There we go. Notice how the x-axis just kind of disappeared because I'm looking right down the end of it. And notice the limit up here, this is 3 up here. These are marked by halves right now. You can see it better down here. So that would be 1/2, 2 halves, and a little bit more. So 1 and a little bit more. 1 1/3, 4/3 was the limit we got by hand. So as I look straight down the x-axis, that limit as we go towards 0 of 4/3 seems reasonable. Now what if I look down the y-axis? I'm going to rotate this again. And here comes my y-axis. And again, my goal is to look straight down that y-axis. So I'm going to try and rotate this till the y-axis kind of disappears from view. It's just a tiny little dot there. That's not bad. And again now, notice at 0, we're down here. This is -3, -2, -1. I didn't quite have it disappeared enough. There we go. Our value by hand was -1/2. This looks maybe like it's not quite up that high, but I trust what we did by hand. If I rotated it just a little bit more, you can actually see, I guess, that we're going up there towards -1/2. So by looking straight down one axis or the other, you can actually see those limiting values on the graph. All right. We won't necessarily look at a graph for every single one of them, but let's look at a couple more of these because it does take a little bit of an art to choose the paths well. So in part B, I'm on page 19 now. Part B, I've got the limit of this function as xy goes to 0, 0. On my domain, 3x squared plus y squared can't equal 0. And again, since those are both perfect squares, unless they're both 0, this is going to turn out positive. So the only bad point would be 0, 0. It's the only thing that'll make 0 in the denominator. So I've got that missing point again, and my domain would be everything else. All right. It worked so well that last time. Let's try this again. Clearly we're approaching 0, 0, which is our missing point. It's really our only boundary point, but that's what we're approaching. So let's go ahead and say I can tell right away that's going to be 0 over 0. I'm not even going to waste the space to write it down this time. I know I'm supposed to prove that this limit doesn't exist. Let's try some different paths. It worked really well last time to try the x and the y axes, so let's do that again. Let's go ahead and start with the x-axis. I'm going to approach 0, 0 along the x-axis, so path 1. The x-axis, or y equals 0. Rewriting my limit. But plugging in y equals 0, on top I would get 4x times 0. On the bottom, 3x squared plus 0 squared. So of course the top, 4x times 0 is 0, and the bottom I have 3x squared. 0 over 3x squared can be simplified to 0 before we plug in the value of 0. Keep in mind this is approaching 0, not at 0 right now, so it's okay to simplify this fraction to 0. Okay. I need a contradiction to that. Let's try the y-axis next. So path 2 is our y-axis. Or x equals 0. And I'll rewrite my limit. On the top, I'll have 4 times 0 times y. And on the bottom, 3 times 0 squared plus y squared. The numerator is going to be 0 over the denominator y squared. Again, before I even take the limit, I would simplify that to 0. So I was able to get a limit both times, but here's the problem. It didn't do what I needed, right? My goal is to get a contradiction here to show that the limits from different directions are different. And I actually got the same answer. So I need a different path. I'm going to need a path 3. You can choose any path as long as it leads or contains that point 0, 0. It wouldn't do it any good to pick a path up here, right? I got to pick something that's going to go through 0, 0. What if we just try y equals x? The diagonal right here. That's certainly another path. Let's give it a shot. I'm going to rewrite my limit again. And I would get, and I'm just going to go ahead and I'm going to replace all the y's with x's. You can do it the other way around, replace all the x's with y's. It doesn't make any difference, but I'm going to replace the y's with x's. So I'd have 4x times x over 3x squared plus x squared. That gives me 4x squared over 4x squared. And now I can simplify that to 1. So there's my contradiction. I got 2 different results, 0 sometimes, and another time I got it equal to 1. So contradiction tells me that the limit does not exist. All right, how can you do a good job of picking paths without having to try a million different things? Take a look at what happened here. Did you notice that the path that gave me the contradiction was the one where the power turned out the same on the top and the bottom? It allowed me to simplify in a different way. Keep that in mind because that can be really key to choosing a good path to get a contradiction. Oftentimes just letting your first path be along an axis is great, establishes a baseline. But to get the contradiction, look for the path that's going to give you the same power of x on the top and bottom. Let's try that out in C. By the way, you can graph these. I'm not going to take the time to do it right now, but you can certainly graph any of these on Maple. It's kind of interesting, in fact, to do that. All right, so for part C, we've got another function. We've got a very similar situation with the domain. X squared plus y to the 4th cannot equal 0. But once again, unless x and y are 0, both of them, those are both positive values. So the only time that that would actually equal 0 would be if x and y were both 0. Oops, wrote that backwards, but that's okay. xy is not equal to 0, 0. So same domain as last time. I omit the origin, and the domain would be everything else. All right, I'm going to go ahead and pick a path that is along one of the axes first, because that usually gives me something good to start with at least. I gotta have something to contradict, right? So let's just go ahead and pick the x-axis first again. Boringly predictable, I know, but gotta get something. So path 1, x-axis, y equals 0. Write my limit. And let's see, if y is 0, I would have 3x times 0 squared over x squared plus 0 to the 4th, which makes the entire numerator 0 and the denominator x squared, which does simplify to 0. So there's one path. I now need to get a contradiction to that 0. And without even writing it out this time, you can probably see I'm not going to get it along the y-axis. If I let x be 0, the numerator would be 0 again, right? I'd actually end up getting 0 over y to the 4th. That'd just give me another 0, which doesn't do me any good. So let's pick something else. I'm going to go back to that idea that if I can get the numerator and the denominator to have the same exponent, it allows me to simplify differently. Looking at this, the highest power I see in here is y to the 4th. So I'm going to think, is there any way that I could make every single term be to the 4th power? Well, if I were to let x equal y squared, that would give me y to the 4th, right? So let's try that as our second path. X equals y squared. Notice our paths do not have to be straight lines. This is actually a parabola, right? X equals y squared would be that parabola there. Oops, and actually I'm going to approach this way though. So I'm approaching the point 0, 0 along that parabolic path this time. Let's try it out. Once again, I'm going to rewrite my limit. Replacing the x's with y squared. Denominator would be y squared to the 2nd power plus y to the 4th. Which is going to give me 3y to the 4th on top, and y to the 4th plus y to the 4th, so 2y to the 4th on the bottom. And now I'm able to divide out those y to the 4ths, so I get a limit of 3/2. Again, there's my contradiction. Since I got 2 different answers along 2 different paths, I can say that the limit does not exist. All right. Once again, I'm sorry these are getting a little bit lengthy, but I've only got one example left to do. So rather than making another whole video for it, let's forge ahead and finish our last example. You might be asking, well, aren't there some times when I can't do any algebra and yet the limit actually does exist? So it doesn't matter how many different paths I try, I'm never going to find a contradiction? The answer to that question is yeah, that actually does happen. And I'll give you an example of a problem where it does and talk about one method to deal with it. In example 6, we're once again approaching 0, 0. Notice that would be the only bad point again. And here's my function. I claim that it actually doesn't matter what path you choose. You're going to get the same answer every time. I'm only going to try one path just to show you what I mean. And then we're going to go back and talk about this method that I've shown you here in the headline. So let's go ahead and say, yep, once again, our domain is just going to be missing that point 0, 0. And the domain would be anything else. If I go ahead and approach upon my usual first choice of paths, the x-axis, I'm just going to call this the path because I'm only going to do one this time. I would get the limit as xy goes to 0, 0 of x squared plus 0 squared plus x squared times 0 squared over x squared plus 0 squared. Everything over here is 0. I really just have x squared over x squared. which simplifies to 1. Now, I'm not going to take the time to do this right now, but I'm just going to tell you that actually, no matter what path you pick, I think you're going to find that you get that exact same result every single time. You're always going to get a 1. I'll encourage you to experiment with that and see it, but I'm just going to note, if you try other paths, you will always get 1. So about that time, we begin to get suspicious and say, well, maybe the limit really is 1. The problem is, trying paths, you can never actually show that a limit does exist. You can show it doesn't exist by getting a contradiction, but because there's infinitely many paths, you can never try all infinitely many paths to show that a limit does exist. So we need another method. This isn't going to work every single time, but there are enough problems where it does work that it's helpful. Sometimes it's helpful to change to polar coordinates. Typically, this is most helpful when you have a lot of x squared plus y squared terms running around, because x squared plus y squared simplifies so nicely to r squared. These are just your typical rectangular polar conversion formulas. I'm sure you've seen them before in Calc 2. It's just a reminder of them. And I'm going to go ahead and say, let's use those to convert to polar coordinates. I'm going to take my limit, and I'm not going to write anything under there for right now. We'll talk about that in a minute. But I'm just going to notice that I have an x squared plus y squared on both the top and the bottom. So both of those can become r squareds. And then this I'm going to have to write out. X squared would be r squared cos squared theta times y squared, which would be r squared sine squared theta. And notice that if x and y are both going to 0, x squared would be 0, y squared would be 0. That means r is going to become 0 as well, right? So if x and y are both going to 0, I can also say that r is going to 0. I can't really say anything about theta. Hopefully that's going to turn out to be okay. We'll see. All right, let's simplify this a little bit. I'd have r squared plus r to the 4th cos squared theta sine squared theta over r squared. And I could factor an r squared out at the top. Which allows me to very nicely algebraically divide out those r squareds. And now if I let r become 0, I'm going to get 1 plus 0 squared times these trig functions, which I don't really care too much about anymore because they're now multiplied by 0, right? And I'm just going to end up with a limit of 1. So again, it's not a panacea for every problem, but it works often enough that it's a good little something to have in your bag of tricks. Sometimes changing a limit to polar coordinates is going to allow us to actually evaluate that limit. All right, that brings us to the end of section 12.3.